Hi guys, I saw this problem about alpha decay. I think it's very interesting. So this is polonium that decays in lead, and also we have some. This is the alpha particle, right? So the polonium at the beginning is at rest, and as a consequence of the alpha decay, we are going to have two velocities, and the velocity of the alpha particle and the velocity of the lead, which is a different sign. So, well, here we have the masses and as what is the change in the linear momentum and the kinetic energy of the polonium compared to the linear momentum and the kinetic energy of these two particles combined. Well, the linear momentum is the same. At the beginning is at rest, and this is like an explosion. So, the beginning of this linear momentum is zero, and in the other part, the linear momentum is going to be zero too, and actually this the linear momentum of the alpha particle is going to be just the same but with different sign, opposite sign of the lead. And of course the kinetic energy is different because the polonium doesn't have kinetic energy, but the alpha particle and the lead, they have kinetic energy, they have velocity, they have masses, so they do. Well, you can see this in the book. They have something more interesting. There's about this example 30.7 in page 165, that also you have this is the uranium decay, and also they have alpha particle, and so they're going to have the same velocities, the same linear momentum, sorry, with opposite sign, and actually you can compute what is the kinetic energy of one respect to the other, just plugging in the formulas of this, the linear moment, this is due to the linear conservation of linear momentum, and you can get this formula that kinetic energy of the alpha particle equals to the ratio of masses and the kinetic energy of the daughter particle. Okay, so this is very interesting. Then they ask how much energy is released. Well, we saw in class that the disintegration energy is in this case it would be the mass of the polonium minus the mass of the alpha particle minus the mass of the daughter. And in this case they use the units are U, so we have to multiply by this, 131.5, and we are going to have it in the million electron volts. And the last part, they say that they say that 1 second. Yeah, they say that if let's see that it disappears. Okay, if the half-life is 1/7 seconds, the probability that any polonium decay in 1 second, what is that? So, well, we saw that the half-life is well, we saw the definition, we saw also how it works, but in this case you have to solve it a little bit different. You have to realize that half-life means that in the 1/7 seconds the population is going to reduce half, right? It's going to be, so in the beginning we have n, and then we're going to have n/2 in 1/7 seconds. Well, so what is going to happen the next 1/7 seconds? You are going to have half of that, which is n4, and then next half-life seconds, like 1/7, we are going to have n/8, which is 2 to the third. So once you have the 7/7 seconds, so 1 second, you are going to have n/2 2 to the power of 7, which is around 0.008, and this is the number of the number of elements we have at the beginning. So the probability of any of them decay is 1 minus that, which is 99.2%. Okay, so this is a very interesting problem. I want to comment with you guys, and I hope you know how to solve it. I'm going to send more problems, and okay, so that's it. So bye bye.